All right. Chapter 14, Section 3 has to deal with population density and distribution. This talks about uh, how spread out a population is, the reproductive strategy, and then how dense that population is. That means how many organisms per unit area, but we'll get more into that. Population density is the number of individuals that live in an area. This is measured by individuals per space. For example, New York City has quite a big population density for humans, whereas a rural farmland will have a much smaller population density. And scientists can figure out the population density, and they'll tell you a lot of things about that area. And the way you measure it is as individuals per unit area. They could be a clump dispersion. These are different types of dispersions geographically and how these organisms are spaced. So, uh, and these pictures are kind of neat way of looking at it. Clump dispersion, uniform dispersion, and random dispersion. So a clump dispersion is more like how people eat lunch in a school, where they sit in little groups. They kind of sit real close to each other, and in general, not everyone's evenly spread out. Like in a uniform dispersion, that would be like a testing environment where people are seated in very specific patterns that are maximizing the distance between them, etc. Random dispersion is what it sounds like. There's no real rhyme or reason behind it. It's just kind of uh, put out there. Here's another good example of a clump dispersion where you have fish. Fish and other herd animals tend to stay together as much as they possibly can, and they'll stay together and stay together and stay together. The nesting patterns could very well be uniform because if you put your nest too close to a bird, it will actually try to peck at you if it can reach you. And if it can reach you and it can peck at you, then you either have to move or get pecked at. Now, I don't know why a sloth is random. Sloths are pretty random to begin with, so I guess that works. But it's just that they do not position themselves relative to each other in any real specific way. Survivorship curve is this idea of how many organisms are surviving or the number of surviving members over time. And you would do it from birth. So from 0 to 5 years, you have a 97% survival rate. And you would go all the way. This thing seems to hit 21 to 25, and it goes 80%. Now, we have a survivorship curve as well as humans. You can look at it in terms of the most common causes of death versus or the survivorship for a certain set of years. That being said, everything that's alive will die. There is no thing that continues indefinitely that we know of. So that will happen. The survivorship curve can be a type 1, 2, or 3. Type 1, low level of infant mortality and an older population, right? That's the healthier of the three. Type 2, survivorship rate is equal across all stages of life. That's 2. And then 3, high birth rate, high infant mortality. So it goes, type 1 is low death rate to high death rate, right? Type 2 is it's even throughout. Type 3 is high death rate to low death rate. And some of you might be thinking, well, why isn't there one that's high to high? Well, high to high would be dead to dead. And though if there was that much death surrounding a group of organisms, they would probably just die off anyway. So that really wouldn't work for any organism. But if you're in one of these two major groups, uh, it would be important to be able to, narrow down how you're going to, uh, like, what it is you're looking for in a population. If you want that population to survive, I would suggest more of a type 1. If you want to see fast evolution, fast natural selection, perhaps type 3. And that is it. No, not. And then here's a graph. Okay, this is good. So here's your type 1, right? Flat, 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 right? Older, 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 and then the survivorship plummets. Here's even for both. And in the blue one, it's a type 3 where you have fewer and fewer and fewer and fewer. And then as it flattens out, you end up with the same number of survival of lifespan, if you will, at the end. So in the end, everyone ends up with everyone dying. That doesn't change. But what's different is how you get there and your ability to adapt to an environment should things change. And that's it for chapter 14, section 3. Let's see this. Let's me stop it.